Okay, in this video we're going to learn something new. We're going to learn how to solve equilibrium problems when we don't have all the information. Usually we don't know everything we want to know, that's why it's a problem. So we're going to be working with the packet that you hopefully picked up yesterday before you left. I also have posted those pages on Google Classroom, and there is a slide that says how to solve equilibrium problems. And it looks like this. So just take a second and read through this, and then you can pause the video, read it, and I will also tell you that what we're covering today is in the book on starting on page 628. It's called Solving Equilibrium Problems, section 13.6. That's also another reference for you. Okay, so hopefully you've read through this page, and we're going to be working with this packet, which is new, and also we're on in the original packet that I gave you, we're on page 22. So I'm kind of going to go back and forth starting from pages 22 to 24 of the old packet and this new one. And what we're focused on is if we need to find the value of K, we don't have it, but we have some concentration information, or if we have K and we need to find equilibrium concentrations, or if we know equilibrium concentrations and K and we need to find initial concentrations. So these are the problems that we'll be solving, and we're going to use these steps. And let's go ahead, and I'm going to write it on the next page. The quadratic formula, you may have to use that, so let me make a new page. Okay, so now I'm going to work problem number 2 in your new packet, and it's at 2000 degrees Kelvin. K equals 2.4 times 10 to the third for the following equilibrium. And if the initial pressure of the nitrogen monoxide is 37.3 atmospheres, determine the equilibrium partial pressures of the other 3 gases. And I've changed this problem slightly. In the packet I gave you, it says determine the equilibrium concentrations, but then you'd have to convert from the one K to another, and I'm not going to make you do that. So we're going to find the equilibrium partial pressures. And we're going to do that by making a table. And notice this is we're going to follow our steps. This is a different problem. On the previous one we had to find K. Now we're being asked to find the equilibrium partial pressures, which is the same as finding, if you were working with molarity, the equilibrium concentrations. So we have a balanced equation for the reaction. That's step 1. That's checked off. We're going to write the equilibrium expression. So I'm going to write that down here. K will equal N2 O2 over NO, and that'll be squared. My third step is to write down, it says the initial concentrations. My third step really should be to make a table and put in everything that I know. So I'm going to make a table. I have, initial, change, and equilibrium. And all I know is that I have 37.3 atmospheres of this. So I'm going to write that in. 37.3 atmospheres of the nitrogen monoxide, and since they don't tell us we have any of the products, because sometimes you do, but they don't say we do, so we're going to assume we don't. So this is 0 and this is 0 initially. Now I'm going to look at my change. What's changing in this reaction? Well, every time the reaction takes place, I'm losing 2 moles of the nitrogen monoxide are decomposing. So I'm going to put a minus 2x in my change here. And every time this reaction takes place, if you think of it that way, for every 2 moles of this that decompose, we make 1 mole of this. So I'm going to put plus 1x here, and for every 2 moles of this that decompose, I make 1 mole of this, so I'm going to put plus 1x here. So now I can put expressions in, or calculate equations for my equilibrium concentrations, or partial pressures, which is what I'm asked to find. This will be 37.3 minus 2x So on the next page, I'm going to substitute these values into here, and this is 2.4 times 10 to the third. And then we'll solve for x, and we're going to have to use the quadratic formula because x is pretty big, so it's going to make a difference to this number. We'll learn that sometimes we can disregard this, but not today because it's too big. It's going to really make a change here. So let's go to the next page. So there's my equilibrium expression, and I changed 2.4 times 10 to the third to 2400. And now I'm going to substitute my values in for these things. So N2 is x, so that will be, this is going to be x, and will be x, so that's going to end up being x squared, x times x. And in the denominator, I have, what do I have? I have 37.3 minus 2x, and that whole thing is squared. So now I'm going to get rid of my fractions, and I'm going to have, I think what the first thing I'm going to do is expand this polynomial. So let's do that. And eventually, when you have to use the quadratic, you can create a, what do you call it, a macro or a program in your graphing calculator to use the quadratic, but we're going to do it longhand right now. So we have, 2400 equals x squared over, let's see, 37.3 times 37.3, which is 8400. And then we have, hold on a second, this is where I made my error. So this should be minus 149.2x, and then we have plus x squared, I think. Did I make another mistake? I did. Let's change this. This is wrong here. This is after you multiply it. This should initially be 1391. Let me double check that. Yes, that's correct. So now we have this ugly polynomial down here in the denominator. And so now I'm going to multiply both sides by this polynomial to get it out of the denominator. So I'm going to end up with 2400 times 1391 minus 149.2x plus x squared equals 0. And even when you're working, you have to do this no matter what. Even if you're going to use the calculator instead of the to solve the quadratic formula, we're not at that point yet because we have to multiply. We still have to multiply this by this before we can figure out our a, b, and c for our quadratic. So we're going to do that right now. 2400 times 1391 is, I hope it's 8400 minus 358080 x plus, oh wait, I did make a mistake, 2400 x squared, and this is not 0. So that's this side, but this was not supposed to be 0 yet. We multiplied both sides of this by this denominator, so on the right side we still have x squared over here, so I'm going to put x squared there. So this equals x squared. So now we're going to subtract x squared from both sides to put 0 on this side. So you can see algebra is coming in really handy. So now we have, I'll rewrite it in red, 333 and 8400 minus 358080x plus 2399 x squared equals 0. Now this is where, if you had a program in your calculator, this is your ax squared plus bx plus c is what we can use the quadratic form. I have it written backwards. This is our b in front of our x, and this is our c. And b is negative here. So we can substitute this into the quadratic. which I did on another piece of paper. So now we're going to use the quadratic formula to solve for x, because once we get x, don't forget we have to substitute that back into our, well, we'll know what our N2 and O2 are, and we'll have to figure out our 2 and O. So let's do that on the next page. So we should have x equals minus b plus or minus b squared minus 4ac over 2a. So I'm going to have x equals minus b, and my b, if you were writing this down on the paper, is, that's negative 358,080. So this becomes a positive. And I'm going to do this twice. So I have plus b squared, which is 358,080 x squared. So that's 1.28 times 10 to the 11th. That's an 11. Minus 4ac, and A is 23.99, and C is some ridiculously large number. C is, where is C? 8,400. So let's multiply 4ac. 4 times 2399 times 333,840, and I get 3.20 times 10 to the 10th. So, and that's going to be divided by 2 times 23.99, 2 times, which is 4,798. So we can simplify this, and we still have to come back and do the minus one here. This is just the plus part. So I have x equals 358,0, this is an 8,8080, plus the square root of 1.28 times, nope, having calculator problems, 9.596 times 10 to the 10th, all over 4,798, and we're going to need the square root of this, so x equals 358,080 plus second square root, this ridiculously large number, and I get 309,781, really should be rounded to a 2, divided by 4,798, and now I'm at the point, I'm going to go, let me copy this. So because the quadratic has the plus and minus of a square root, I can now figure out my two roots. So this is this plus 358,080 divided by 4,798, and this ends up being x equals 139, which is disturbing. I'm wondering if I made another mistake somewhere. Anyway, let's figure out this one. X equals 358,080 minus 309,781 divided by 4,798. Much better. This is 10.06. So this one is possible because when we go back to our table, if you remember, if you look at your paper, the concentration of the nitrogen monoxide at equilibrium is equal to 37.3 atmospheres minus x. And we could not plug this number in for x. So this one doesn't work. There'll always be two roots, but usually one won't work. So this is our x. So now, for our equilibrium concentrations, we have our initial or change. This is 37.3 minus x, so this is 37.3 minus 10, so this is 27.3 atmospheres. And for our N, this was our NO, our N2 plus our O2 These were X and X, so these are 10 atmospheres and 10 atmospheres. That takes forever. So what I'm going to show you now, I'm not going to talk anymore because I think this has gone on for over 20 minutes, but I have solved the other problems in this packet and the other one, and I'm just going to post the answers. And you can work them and then look at them. I don't think I made mistakes on those. And then bring your questions to class. This is problem 1 from the new packet. This is the third problem on the new packet with some scribbles from the one that we just worked. This one is on page 23 of the old packet, and notice the quadratic formula was not required here. You were given equilibrium concentrations, and you had to find out the missing one by using stoichiometry and your K value. And this is the problem from page 24 of the old packet. Bring your questions to class, and you do have homework. I had posted that in the Google Classroom above. So copy the quadratic formula down because we may have to use it. So, moving onward. So again, we're going to first start trying to learn how to calculate, oopsies, sorry about that, calculate K when only initial concentrations or even only some of the initial concentrations are known. And no matter if we're figuring out K or figuring out concentrations, we're going to create a table. And I call these tables rice tables. The book calls them ice tables. R stands for reaction. I stands for initial. I'm going to write it over here because I can't write that tiny. Initial. C stands for change. And E stands for equilibrium concentrations. So you have initial concentrations and equilibrium concentrations and your change between them. And we're going to use stoichiometry to figure this out. So let's just look at this problem as a teaching example. A closed system initially contains 1 times 10 to the negative third molar H2, and it's molar. We're interested in concentration, so it should be in molarity or in pressure. And it contains 2 times 10 to the negative third molarity iodine gas. At 448 degrees Celsius, because equilibrium is dependent on temperature, it reaches equilibrium. An analysis of the equilibrium mixture shows that the equilibrium concentration of the hydrogen iodide, the product, is 1.87 times 10 to minus 3. We're asked to calculate K at this temperature. So if we follow along on the page that I asked you to read before, the first step is to write the balanced equation for the reaction. Now they have written that for us, so that's done. Step 2, write the equilibrium expression or the law of mass action. So I'm going to write that down here. K equals blah, 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 blah. HI squared over the concentration of the hydrogen times the concentration of the iodine. So if I have that, if I need it. Then we're going to put in our initial concentrations. And we're actually going to put in everything that we know. So this is why, let me see if I can. So here I have put in for the initial concentrations. So let me just change my pen. We have the initial concentration. So the initial line is where you write your initial concentrations. I write my initial concentration of the hydrogen below the hydrogen. I write my initial concentration of the iodine below the iodine. Now notice there's a 0 here because initially, if I'm starting with products, they didn't tell me, I'm starting with reactants, and nobody said that we were going to have any products in our system. So this is 0. If they don't say there are any products, you assume that's 0. So on step 4 of your list of things to do, it says calculate Q and determine the direction of the shift to equilibrium. Now, we could calculate Q, but we can't determine the shift because we don't know K. So we're going to skip that step and go to 5. And 5 says define the change needed to reach equilibrium and define the equilibrium concentrations by applying the change. So this is where we use stoichiometry. So what is changing when the reaction happens? Well, this is where we look at the coefficients, and only 1 mole of hydrogen is going to react in this reaction at a time. So I'm going to say minus x, minus 1 mole, or minus 1x, is the change for the hydrogen. Each time this reaction takes place, 1 mole of hydrogen will react with 1 mole of hydrogen to make 2 moles of hydrogen iodide. So I have minus 1x for the hydrogen and minus 1x for the iodine. And when this reaction happens, you'll make 2 moles of hydrogen iodide for every 1 of hydrogen that's used. So this over here says plus 2x. This is a molar ratio. We're using stoichiometry. For every 1 of these that is used up or goes away, we make 2 of these. So on our change line, we're putting in x's and multiples of x's. Minus 1x here will make 2x of this, and that just comes from the coefficients. Now we're going to do the second part of step 5. We're going to apply this change to our initial concentrations. Initially we had 1 times 10 to the negative third, but at equilibrium we will have 1 times 10 to the negative third minus x. Now I filled this in, but we need to do a little more work before you can know how I filled that in. For the iodine, our equilibrium concentration is going to be 2 minus x, 2 times 10 to the, so I could take a red pen and write down here, this, before I calculated that number, I had in here 2.00 times 10 to the negative third minus x, in parentheses, I'll just put that. And what I had, I'm going to write this part in black, what I had in this box was 1.000 times 10 to the minus third minus x. So before I filled these in with numbers, which I did while I was watching the Super Bowl, I had these numbers there. Now let's look at our product column. We started out with 0, but we know we're going to make 2x. And they told us what our equilibrium concentration was here, so that was really necessary, because otherwise we wouldn't have been able to solve this problem. They say our equilibrium concentration is 1.87 times 10 to the minus 3, so we filled that in. So I know now that 1.87 times 10 to the minus 3 has to be equal to 2x, because I started out with 0, I added 2x, and that's going to equal my equilibrium concentration. So that's what I've written down here. If 2x equals 1.87 times 10 to the minus 3, then x has to equal 0.935 times 10 to the minus 3. It's algebra. So to figure out these numbers, I took my x, and I substituted in here, and I subtracted, and that gave me my equilibrium concentrations of each of these. Once I have my equilibrium concentrations of each of these, I was asked to find K, so we're going to do that on the next page. So again, I had already written my my law of mass action, my equilibrium constant expression. I'm going to take the values that I just put in my table, my equilibrium concentrations, and substitute them in. So here now I've substituted them in, and then I will enter this into my calculator. Now please be careful working with exponents in your calculator. This top numerator is this thing, which I'm now going to put parentheses around, all of this squared. So you not only have to square the 1.87, but you have to square the 10 times minus 3. So put this in parentheses in your calculator. And what you should find is that K equals 442.6. A very big K. So there's going to be, that's why there were so many products, and the reactants had a tiny concentration at equilibrium. These are the steps you're going to take to find K, or find initial concentrations. So we're going to do another type of problem now.